Today we are going to take a look at a rather unusual decay chain. The decay chain of Protactinium-231, which is known from the Uranium-235 decay chain. Normally I always ignore the Uranium-actinium series, as Uranium-235 accounts for only 0.72% of all uranium atoms, but today it's responsible for 100% of the activity. The rarity of the decay series is also the reason why chemical separation based on one of the nuclides it contains is required. In this case, it's the longest-lived Protactinium isotope 231. This was purified from several tons of spent nuclear fuel back in the 1960s, and these approximately 100 grams still are the majority of the worldwide Protactinium stocks available to nuclear laboratories. Similarly, the laboratories of the Institute of Nuclear Chemistry in Mainz have a radon-219 generator containing some Protactinium-231. This contains 10 milligrams of Protactinium-231. The danger posed by sources containing, for example, Protactinium-231 or radium-226 is that they emanate. Emanation is the technical term for the production of radon isotopes through radioactive decay. In the case of Protactinium-231, this proceeds via actinium-227, thorium-227, and then via radium-223 to radon. This series is not yet in radioactive equilibrium, which means that the Protactinium source will emanate even more over time. But so what? Well, radon is a radioactive gas. In the case of Protactinium-231, the isotope radon-219 is released. Obviously, inhaling radioactive gas is not a good idea, but as a gas it can easily disperse if stored improperly and, well, be radioactive. Due to the recoil of the radioactive decay of radon, the still radioactive daughter products are dispersed through the area and can thus very easily contaminate rooms. And it's precisely this emanation that we also use in the practical experiment to generate activity for our experiments. Accordingly, in the following we will examine the decay chain of Protactinium-231 only after radon-219. There will never be any direct contact with Protactinium. So, for our experiments, we have the following nuclides and decays available, which we can examine in a little bit more detail. Polonium-215, unfortunately not. With such a short half-life, it's unfortunately out of the picture, but we do have lead-211, which, as we can see from the blue tile color, can undergo a beta- decay into the more short-lived bismuth-211. We will look at the production of bismuth-211 from this decay. From the isolated bismuth-211, we can record a rather interesting alpha spectrum. The alpha decay of bismuth-211 produces the beta- emitter thallium-207. And we can also investigate this product. Furthermore, thallium-207 is radioactive and decays into stable lead-207. And we can also experimentally verify its half-life of 4.77 minutes. These experiments form part of the nuclear chemistry practical course and for reasons of time efficiency are not carried out in the chronological order of the decay chain. I will display the experiment numbers below, but list the experiments in accordance to the decay chain for this video. We obtain the activity for the experiments via implantation using a large nickel sheet. The emitted radon spreads throughout the desiccator, at the bottom of which is the Protactinium located. And this radon decays into polonium. There is so much energy behind this decay that the polonium effectively gets stuck in the sheet. But additionally, I would not rule out electrostatic effects due to recoil ionization that traps more ions on the nickel sheet. Of course, there is the next alpha decay that can eject the subsequent daughter nucleus. So this is all a very dynamic process. But after 30 minutes we have ultimately implanted sufficient activity of the relevant radionuclides. Now there's lead-211, bismuth-211 and thallium-207 in the nickel plate. This plate is leached in hydrochloric acid, causing the nuclides to dissolve. This is done using 12 milliliters of 0.1 molar hydrochloric acid heated to its boiling point. Some bismuth-211 may remain on the plate. The plate is leached again in another beaker but ultimately combined and thus homogenized. This allows us to extract further activity for the experiments. This solution is distributed among the students. And now we have 3 chemically distinct elements and radionuclides in our solution. Well, then let's take a look at some various decays. First, the beta decay, which produces bismuth-211. In other words, we are now carrying out all of this chemistry to isolate pure lead-211, so that we can then track the decay of bismuth-211 on a silicon counter. Experiment number 1. A carrier solution is made using 10 milliliters of water and a few drops, approximately 7 drops of some inactive lead nitrate carrier solution and 1 milliliter of 2 normal sulfuric acid. Here we can already see how slowly inactive lead precipitates as a white lead sulfate precipitate. Normally one always adds the carrier to the inactive substance and then allows both to precipitate. However, that does not work here, and we need some pre-precipitated lead sulfate as we want to observe precisely this reproduction of bismuth. And then, if we have to wait for this precipitate to form completely, we will miss the bismuth reproduction. So we give this slow precipitation a slight head start to allow sufficient material to form so that we can now add half of the given solution to this carrier solution. This means we have now precipitated the existing lead-211 with some inactive so-called isotopic carrier. Without inactive lead, pure lead-211 would never have precipitated as a sulfate. More on this in that video. As lead and thallium have now entered the lead sulfate solution and thallium sulfate is soluble, the suspension can just be filtered. The lead-211 remains trapped in the filter paper thanks to the lead sulfate carrier and can then be quickly measured. We should be able to observe that the activity of the measured sample will first rise and then fall again in accordance to the half-life. But we are measuring using a silicon detector. This makes use of the high ionizing power of alpha rays, so we are not able to measure lead-211 directly on the detector, as this is a beta-minus emitter. And for all practical purposes, an alpha counter does not measure beta radiation. Any measured values will originate from the activity of bismuth-211, which, however, is determined by the activity of the parent nucleus, lead-211. So what do we see here? A typical activity spectrum consistent with a transient radioactive equilibrium. So we have just gone to a great deal of chemical trouble to obtain the purest possible lead-211 sample from this mixture of radionuclides. In a world where all students worked perfectly and took 0 seconds, we wouldn't measure anything at the very beginning since we have a perfect lead-211 and can only measure bismuth-211. The decay of lead-211 then produces new radioactive bismuth-211. Due to the formation of short-lived bismuth-211, the activity rises rapidly and then falls slowly as the parent nucleus is not that long-lived and the decay has a noticeable effect on the amount of bismuth-211. Over time, this decay means that we have less lead-211, which in turn means less bismuth-211 that can be formed, and so the activity slowly decreases. In the later part of the activity curve, the decline therefore follows the half-life of lead-211, and the incline in the earlier part follows the half-life of bismuth-211. So you really have to work quickly, otherwise you won't see this rise and then you won't be able to determine the half-life of bismuth-211. Directly from this curve you can obtain the decay constant, but this can simply be converted into the half-life. Here I arrive at 1.5 minutes, which is already clearly off, but especially at the start it may well be that you only start measuring too late because of sample preparation, and so the measurement only begins here. And you really need the incline to determine the half-life. For the later part, one could then determine the half-life of lead, which comes out to 34 minutes. One was able to demonstrate the transient equilibrium whereby the measured total activity consists of the bismuth-211 formed by the steadily decreasing amount of lead-211. And now let's take a look at the bismuth-211 decay. We have just used half of the nickel sheet in HCl solution. We left the other half to stand for 10 to 20 minutes so that the dissolved lead-211 could form bismuth-211. To this we add 10 milliliters of water and a few drops of lead-bearing solution and brought it to a boil. A nickel sheet was stripped of its oxide layer using concentrated hydrochloric acid to remove, its oxide layer and add it to the boiling active solution. After 2 minutes, we had electrochemically deposited some of the bismuth-211 onto the surface of the nickel. Both bismuth and lead are more noble than nickel and could be deposited, therefore inactive lead was added as a carrier to prevent the active lead from adhering. At the Geiger-Müller counter, beta activity is measured, and here we assume that we only have bismuth-211. At time 0, thallium-207 will be formed through the radioactive decay. Initially, the half-life of the parent nucleus plays a greater role. However, after approximately 20 minutes, i.e. 10 half-lives of bismuth-211, none of it remains, and for all practical purposes we are left with only thallium-207, which, due to its longer half-life, remains available for measurement for a little while longer. From this, a half-life of 4.4 minutes could be determined in my case. In this context, it is important to note, in a perfect world, we would have only pure bismuth-211. But no, unfortunately, we have some lead-211 clinging to it. This distorts the measurement values by keeping bismuth-211 alive longer and above all influencing the measured activity at the very end. The final values must therefore be treated as bismuth-211 and extrapolated backwards as a background level 2 times 0. This is then used to correct all of the other values. Otherwise you won't get a half-life of 4.4 minutes. Experiment number 3. Bismuth-211 decays into thallium-207, and we've just examined that quite closely, but we can investigate the decay of bismuth-211 in even greater detail. So you have to do the whole thing again as best as you can, because you never actually separate out all of the bismuth activity, and some has already formed up again. And then you can measure this nickel sheet once more, but in this case using an alpha spectrometer. We can see both alpha lines of the bismuth-211 decay perfectly, one at 6.6 megaelectron volts and one at 6.2 megaelectron volts. But looking at the chart of nuclides, I am missing something at 7.4 megaelectron volts. Can someone explain in the comments what I'm hinting to here? So here too, we can determine a half-life by measuring 40 times 30 seconds and twice for each 300 seconds. The later values must again be extrapolated back to t equals 0 using the lead background. Unfortunately, lead sticks to nickel sheets, so without correction the bismuth-211 appears to be longer lived in the results than it actually is. This gives us a decay constant of 5.47 times 10 to the power of -3 per second, or expressed as a half-life, 2.11 minutes. That's almost perfect. So now we have thoroughly analyzed bismuth-211 and will turn our attention to the end of the decay series, thallium-207. Experiment number 4. For this, a glass plate was implanted overnight. As with the nickel sheet, the deposition over the Protactinium-231 source is a highly dynamic process. After one night, all of the radionuclides except radon have reached radioactive equilibrium on the glass plate. If you take this glass and place it with the implanted side facing down onto another piece of glass, something quite elegant happens. Bismuth is an alpha emitter, and during the 5 minutes implantation time, thallium-207 recoil nuclides are fired into the other glass, where they can be measured using a Geiger-Müller counter. Here's an animation of the procedure, and this is what it looks like in real life. Of course, it is important that the correct sides are facing each other, and after 5 minutes the glass plate can already be taken to the Geiger-Müller counter. This whole thing has now only worked because of the recoil during the alpha decay. To calculate the recoil energy, we need the alpha energy, 6.62 megaelectron volts during the decay, which we will confirm later, as well as the ratio of the two masses involved, i.e. 4 for the alpha particle and 207 for the daughter nucleus. This gives us a recoil energy of 0.128 megaelectron volts. Each of the 54 measurements lasts 30 seconds, and there's a 22-second interval between the end of the deposition and the start of the measurement. And there you go. Once you've run it through a fit, you can get a decay constant of 0.0022 per second. ln2 divided by 0.0022 gives us 315 seconds or 5.25 minutes. And if you look at the literature, it's 4.77 minutes. Close enough in my opinion. Experiment number 5. This recoil atom glass plate thallium experiment is the very first experiment in the practical course. All of the groups have now carried this experiment out over the course of this one experiment day. And so you can observe a consistent trend, namely that the initial activity continues to decrease and does so with a half-life of lead-211, since the amount of the glass was fixed after it was removed at the start of the experiment day. And with that, we have now investigated the complete decay series of radon-219. In the first experiment, we showed by recreating the bismuth-211 from the lead decay, we were able to determine its half-life directly from the rise, and the half-life of lead-211 indirectly from the fall of the curve. I say indirectly because the measured values still came from the bismuth decay. In the second experiment, the production of thallium-207 was investigated from the alpha decay of bismuth-211. We were able to determine the half-life of thallium-207 directly and once again confirmed the half-life of bismuth-211 from the decline of the curve. And in experiment number 3, we were able to measure the decay of bismuth-211 directly and thus determine its half-life directly. And in experiment number 4, we were able to confirm the half-life of thallium-207 via the recoil atom experiment. Once everyone had worked together, we were able to indirectly verify the half-life of bismuth-211 yet again via our thallium-207 measurement experiment. And with that, a huge thank you goes out to Yannick Lohmann, who made this video possible, and to Professor Dr. Reich, who is responsible for teaching at the Institute for Nuclear Chemistry in Mainz. Also, a big thank you goes out to all of my patrons for their financial support. And with that being said, thank you for your attention and goodbye.